next speaker is Ziqian Li from University of Chicago. We'll talk about autonomous error correction with two transmons. The floor is yours.
All right, thank you for the introductions. So today I'm going to talk about autonomous error corrections with only two transmons. And this is the experiments done in the Schuster lab by me and the colleague Tanai Roy and also Elliot Caput from Colorado Mines. Okay, so this is the outline of my talk today. First, I will introduce you what is the AQEC protocol we proposed and realized, the star code. And second, I will show the two transmon device demonstration with the star code. So as a beginning, what is autonomous quantum error correction? This is borrowing the idea from the laser cooling. So suppose you have one atom and place it at the ground states, maybe the ground motions of the states. Sorry. All right. So let's say the atom is interacting with the having some interactions with the environment. So the environment will bring some errors to your atoms and bring it not put it jump out of the lowest energy states and maybe some excited states. So the goal here is whether you can find a certain set of lasers that can continuously shine on the atoms and push it continuously back to the ground states. Now, autonomous quantum error correction is doing a similar thing, but a non-trivial extension of it is to try to laser cooling a manifold of states. So this is the block sphere. You have the logical 0 and logical 1. It also has some interactions with the environment that you don't want to happen, but actually it happens and makes the logic states becoming the error states. Now, the goal here is to find a same set of lasers that can continuously push all of the states back to the block sphere. But not only that, you have to make sure that all of the states you pushed back are point-wisely to the correct logical states, but also at the same time, when you apply all of the lasers, the block sphere should maintain its structure. So when you're turning on lasers, the block sphere should not be distorted. And that's the hard part of the autonomous error correction. So it is very tricky to choose the logical encoding, and it's also very important. And here is our star-coded logical states. We encoded our logical qubits into two 3-level systems. We labeled the first 3 levels independently as G, E, and F. Our logical 0 is Fg minus Gf, the entangled state. And logical 1 is FF minus Gg, the other entangled states. So you can view these two states as the Bell states using the G and F basis, the even odd parity Bell states. There are a few necessary properties when you're choosing logical states in order to make it a valid autonomous error correction code. The first is that all of the error states and logical states has to be orthogonal with each other. In our cases, we only consider the single photon loss error happen to the logical states, which means that for both L0 and L1, the corresponding logical error states will have some population on E level, while all of the logical states are only using the G and F level. So by definition, they are just orthogonal with each other. And the second thing is that you have to make sure that your error does not distinguish your logical states so that the error will not distort your block sphere. In these cases, if you have single photon loss error happen in the system, that means you will have to have the same average photon number between all of your logical bases. For L0 and L1, we choose for the star code, they have all the same average photon number too. So they satisfy this requirement. And finally, there is a special requirement imposed by the autonomous error correction, which means that if I assume my error correction operator A, that operator A has to be always commute with my system Hamiltonian H. This can be directly viewed as the system Hamiltonian H doesn't care when you apply the error correction, which in other words, you can continuously apply your error correction to your system. So then you can do whatever like a laser cooling, always push your states back to the logical space. Apart from the logic encoding, another important element is to achieve to correct the errors. We couple our 2-3 level systems independently to a lossy resonators and use the lossy resonators to do the dissipated cooling. We only kept the first 2 levels of the lossy resonators because we think it's code enough, and we try to engineer the E0 to F1 interactions between each 2 qubit resonator pairs. So now whenever you have an error state happen, it will activate the E0 to F1 oscillations. And since the resonators are so lossy, the dissipation will happen very quickly, and it will stabilize the states from E0 to F0, or in other words, you are generating an E to F excitation channel by using the dissipative, realizing the dissipative cooling in our system. Okay, so now it's coming to our protocol. Let's thinking about the first cases. How do we stabilizing certain states, which in our case is the L0, Fg minus Gf. We consider in our system turning on two QQ sidebands, the E to Fg interactions and E to Gf interactions. All of the sidebands has the same rate W. If you wrote out this cases in a rotating frame, the Hamiltonian H red looks like this: W times FGEE plus GFEE plus complex conjugate. This Hamiltonian, if you do the quantization, do the diagonalization, it has three eigenstates, and we can plot it in an energy diagram here. The middle one with the zero energy is our target dark state Fg minus Gf. The other two are our states that has energy around plus and minus square root 2 W. If your W is large enough, those states will be very far away from your target states and will not interfere with our scheme. We can do one more step further is we can introducing frequency detunings in our QQ sideband. So let's say I'm not driving E to Fg on resonant, but however, I'm driving it off resonant by frequency detuning plus nu zero. And I do the other QQ res sideband by frequency detuning minus nu zero. What it does is that it will introducing a time-dependent phases to your sideband interactions in the rotating frame Hamiltonian. You have the e to the minus 2 pi I nu zero t terms appeared. But fortunately, this will not change your target dark states. It will still leave the Fg minus Gf state energy unchanged, form unchanged. What it really does is making the other two unwanted states being fast oscillating, time dependent. And whatever that happens, it doesn't care. It is not having no effect to us. We then add the QR blue sideband to counter the photon loss that will happen to the logical states. We add the E0 to F1 interactions. For example, here, if we have a single photon loss happen to the first transmon, the L0 states will decay one photon become EG. The EG00 states under the interaction E0 to F1, we're oscillating with L010. Now, the photon excitation in the first resonator will decay the excitation very quickly at rate kappa and finally stabilize to L0 in the end. So that completes the error correction cycle. So if we have the QQ sideband rate W being a lot larger than the QR sideband rate omega, and all of the rate here are much faster than the single photon loss rate in the transmon gamma, we can stabilize in one of the logical bases, L0. We can do the same thing for the other logical state L1, which is FF minus GG. We turn on two other pairs of QQ sideband, the QQ blue sidebands, E to GG and E to FF, with the same rate W. In the rotating frame Hamiltonian, it has three eigenstates. One of them has zero energy, is our target logical states L1 with zero energy, and the other two are fast oscillating, are other states that we don't care about and also far away in energy. We can similarly introducing the frequency detunings new one to the sidebands in the system, and it will end up with introducing some time-dependent phases as well to the Hamiltonian. What it does is it will make the other two states oscillating very fast, but still keeping our target logical states being energy unchanged and form unchanged. We add the exactly same QR blue sideband E0 to F1 to our system to counter the single photon loss ever happen in these cases. Now, if I have a single photon loss happen to my logical state L1, it will decay to, suppose the error happened to the first transmon, it will become EF. The EF00 will oscillating with L110 under the QR blue sideband E0 to F1. The resonator will decay its photon very fast and stabilize to L1 in the end. And under the same rate relation, QQ rate, sideband rate being the fastest, QR sideband rate being the middle, transmon decay being the slowest, I can stabilizing my L1. Now here comes the full star code protocol. We call it a star code because it's topologically equivalent to a 4-pointed star in the interactions. What we need is we turn on in total 6 continuously on tones. 4 equally mixed 2-photon QQ sidebands and 2 QR blue sidebands. It will look like this. It's a little bit messy at the beginning, but when you do when you diagonalize the rotating frame Hamiltonian, you will notice that why we need the frequency detuning nu0 equals to nu0 nu1 being introduced in our system. That is because if nu0 equals to nu1, or if you don't have detuning in your system, there is actually 3 zero energy eigenstates. The first two are all logical states. However, the third one is having trouble. It will cause the error correction being problematic. So we want to really remove those states. Unfortunately, to remove this unwanted eigenstates, we only need to choose different frequency detunings, nu0 being different to nu1. And then we will end up with only 2 states, L0 and L1, which is our star code logical basis. The star code aims to correct all of the single photon loss error and suppress all of the low frequency dephasing noise. We can see that also from a different view by drawing out the energy levels. We do a second frame transformation, change the Hamiltonian into the fully rotated frame, and we plotted all of the 9 eigenstates of the 2-3 level systems. Suppose we turn on this 4 QQ sidebands first, and the 9 eigenstates can be grouped into 3 different classes. The first two, L0 and L1, are our logical states with energy plus and minus nu, which is the frequency detuning. The next 4 is our error states, e.g. EF and GFE, which are gapped by half the harmonicity of the transmon. The other 3 is the unwanted straight eigenstates, which we want to push them as far away as possible from our logical states. And as you can see from the energies shown on the left, they are gapped more or less around the value of QQ sideband rate W. So which means if you have a larger QQ sideband rate, those 3 unwanted eigenstates will be very far away from the logical basis. And that is our goal in experiment to push. We then add the QR sideband E0F1 into our system, and that will introducing the oscillation between the error states with the logical states by populating the corresponding resonator. And the population of resonator will decay very quickly, and all of the error states are corrected back to the original logical states. And that completes all of the error correction. Here are some simulation results. I choose the superposition logical states LX at the physical transmon T1 at 20 microsecond. I first choose about 5 megahertz QQ sideband rate, and then sweeping the detunings I choose for the QQ red and blue sideband pairs. As you can see from plot here, I'm showing the logical lifetime of LX after error correction. And along the diagonal lines, you have the lowest correct logical lifetime. This is exactly what we have predicted in the theory, that nu0 nu1 has to be as different as possible. And when they are opposite, you get the best performance. I can also sweep the QQ sideband rate W versus the QR sideband rate omega. And the theory requires that W to be much larger than omega in order for the QR sideband to be treated as perturbation. And that is happening in the simulation as well. About when W is an order of magnitude larger than omega, I got the best performance. When I'm sweeping the physical transmon T1 lifetime, I plotted the improvement ratio over the transmon T1. And you can see here the plot is almost linear, which means that there is a quadratic improvement over the transmon T1. And you can achieve break even with a relatively small T1. So with 10 microsecond T1, you can still see a factor of 4 improvement over the free decay cases. So this is achievable only when you have a very large W. So if you have 10 megahertz W, it's super easy to get break even. And here comes to our device to demonstrate its star code. This is our star code load logical qubits. It has 2 transmons shown in the red color. Those 2 transmons have a shared tunable coupler, providing all of the QQ interactions. And each one of the transmon is coupled to lossy resonators, used also as the readout. The circuit diagram of this device is shown here. You have a shared ground loop between the 2 transmons, which is interrupted by a squid. And we send our flux modulation through the squid to generating the QQ interactions. But for simplicity, you can basically think of the system as 2 3-level systems coupled. Each one of the 3-level systems are coupled to the readout. As a reminder, the device goal is to both actively correcting photon loss error and passively suppressing dephasing error, improving both T1 and T2. The device coherence is here. We have, roughly speaking, 10 to 20 microsecond T1 and T2 for both of the transmon, and about 0.3 microsecond for the resonator decay. First, we demonstrated we can use the coupler to generating all of the QQ sideband needed for the experiment. We do flux modulation at the transition frequencies. For example, if I drive at the E to GF transition frequencies, we can realizing a 21 megahertz QQ red sideband. Here I'm plotting the average photon number read out separately on those two transmons by sweeping the modulation frequencies versus modulation times. So you can see a nice Chevron plot. I can also send that sum of the two transmon frequencies and realizing the GG to E QQ blue sideband, which is 9 megahertz here. I'm also plotting, you can see also nice oscillations with the two transmons happen at 0 to 1. By demonstrating the coupler is working well, we can move one step further, engineering all of the interactions needed for the star code. There are two different parts. The first part is the QR sideband rate, the QR sideband interactions. I drive at the mean frequency between the transmon and the resonator through the charge line coupled to the transmon pad. And by initializing the system to the E0 for both transmon and resonator pairs, I can see a fast stabilization to F0 on the left plot. Here you can see the average photon number starting from 1 quickly after 3 microseconds of E0 to F1 interactions, stabilized it to 2 for both of the transmon. Next, I send all of the 4 QQ sideband interactions through the flux line and prepare the system's initial states to FG. By choosing the FG, it was select the FG effectively FG to GF oscillations in our system. So what you will see in the experiment data on the left plot is that an oscillation between 0 and 2 with opposite phases happen on both transmons. In the third cases, I'm initializing the system to the states GG, and that will select the GG to FF oscillations in our system. And on the experiment data, you can see 0 to 2 oscillations with the same phase happen on both transmons as well. So we have shown that all of the interactions we needed for the star code is properly behaving. We can move forward to the star code demonstration. We separated the demonstrations into 3 parts. The first part is free decay. We prepare our logical states, let it free decay, and measure whatever the coherence is. Second, we turn on only the QQ sidebands. So we call it a QQ echo because when turning on only the QQ sidebands, it will structure the energy spectrum of our of the star code. So it will passively suppressing the dephasing using with the help of the echo effect. This is the value we choose in an experiment, about 1 to 2 megahertz. And finally, we turn on all of the 6 tones in our system, and it will do the autonomous error correction. It will both correct the decay error and suppress dephasing error. And here's the number we use in our experiment, about 1.5 megahertz QQ sideband rate, about 1 megahertz detuning, and 0.4 megahertz QR sideband. We choose the following 3 states, L0, L1, and LX, as our target test logical states, and do state tomography of them. We rotated the density matrix to the real part and show them here. The initial states are shown in the basis from GG to FF. The density matrix looks like this. The preparation fidelity are all about 90%. In the free decay cases, you can see that, especially in the L1 and LX cases, those off-diagonal terms, which indicating the coherence, are completely gone. Which means that our error is happening very quickly. In the QQ only cases, when we turn on only the QQ sidebands, 4 QQ sidebands, you can see the echo effect. Well, all of the off-diagonal terms are coming back, but actually at the cost of populating the other error states on the diagonal terms. So you have more population in your unwanted boxes. Finally, with the AQEC cases at 9 microsecond due to tomography, you see that not only does you have all of the off-diagonal terms coming back, but also you have those error states population being suppressed. And we can do the state tomography at each time points and reconstructed the system's density matrix and calculated the correctable error population. The correctable error population here is defined as the population in those error states. For L0, it's summing up the population in G and EG. For L1, it's summing up the population in EF and FE. For LX, it's summing up all of them. There are three different cases. For the free decay cases shown in color black, you can see error accumulating. In the QQ cases in the color blue, you can see that the error is even enhanced because you are turning external drives, which will causing errors. And finally, when in the AQEC cases, which is shown in green, you can see that all of the errors are being suppressed versus the QQ cases, which is what we expected. And finally, we can measure our logical states coherence. So we choose the following three metrics as our logic states. We use our reconstructed density matrix to calculate the GFFG operator expected value for L0, GGFF for L1, which are actually basically the off-diagonal terms. And we have for LX calculated the expectation value for logical operator X. The logical operator X's look like this. It's a bit complicated, but basically it's the sum of four off-diagonal terms in the density matrix. So we have shown here that we have about 24 microsecond T1 for after error correction for L0, 17 microsecond for L1 after error correction, and about 9 microsecond for LX. So the improvement over uncorrected logical states are separately a factor of 2, factor of 5, and a factor of 1.4. For better improvement, we would really want a stronger QQ sideband rate W and even longer transmon T1. So the crucial part here is that our current QQ sideband rate W used are very small. It's only 1.5 megahertz. If we can just slightly improving that to 2.5 or even 3 megahertz, we will see a much better improvement in our error correction. As a summary, we have proposed and realized a new autonomous error correction code, which only needs 2 transmons and a coupler. All of the stuff are all basically on chip. And as the next step, we would like to try some error transparent gate with the device. Thank you. Here are all of the people contributed to the projects. And I'd like to take any questions.
Thanks a lot for the beautiful talk. Any question?
A few slides from the end. There was one before this, I believe.
Yeah.
Do you have any insight into why, like the black and the blue curves match very well with the data and the prediction? Why does the green curve not match as well?
Yeah, so there are a few problems is that when in our system, our readout are not that perfect. When we turn in all of those drives, our readout are slightly messed up. So especially in the LX cases, you can see that our simulation are not that matched well. It's because of the readout itself. It's not related to the states.
Okay, thank you. Yeah.
Other questions? Otherwise, I have one myself. What about heating?
Yes. So the heating, in fact, in our system is not that obvious. It's not big. So when turning all of the sidebands, we do see a little bit of heating, but not critical. It's not the main error channels.
Despite the drives.
Yes, even with the drives.
Other questions? Otherwise, let's thank the speaker again.